Welcome everybody. Today is the part 2 of the series on distillation columns, especially the challenging ones. Let me introduce you to the speaker. Juan Carlos is our senior experienced APC engineer. He will talk about APC on controlling complex distillation columns. One quick note, we will start a poll here very quickly. We'll start a poll here. Just a minute. The poll says, did you have challenges with APC on difficult columns? Appreciate if you could answer these polls, and we will share these results at the end of the poll. Yeah, hoping to get some feedback from you so that we understand. Give everybody a second so that yeah, looks like everybody answered. So here it is. I'm going to publish the results. You see more than half of you have not installed on APC on columns. So this may be a good one to understand how it is done. And about 1/4 of you have difficulty initially. So let's see what JC can share with you about these difficult columns and APCs. Go ahead, JC.
Okay, Ravi, thank you very much. Well, yes, the topic at hand today, as Ravi has said before, is about distillation columns, but not your, let's say, standard distillation column. Something that, for one reason or another, becomes a little bit more complex, a little bit more challenging. In the previous part of this series of webinars, we explained what has been our approach in terms of base layer control. How have we improved the operations of complex distillation columns, primarily through improvements as well on the base layer control. But then here we are going to talk about the step forward, the next step after that, which is what could you gain even if you have already done some improvements in your base layer? Could you still gain some benefits from your column? So in fact, for those of you who were present in the previous webinar, you could see that we are going to use 2 of the 3 examples that we explained last time. Why only 2 of the 3? Because I would like to go in a bit more in-depth analysis of what was the approach that we took in each one of those cases, and show you what have been the benefits that we have obtained in those cases. So that's why we are going to just focus on those 2 examples. The first example is a methanol water column. Sounds easy enough, but it is really not when you know the details of this column. It's a very high purity column. We will see in a bit. And also we are going to talk about the control on an extractive distillation column and how it actually becomes a bit counterintuitive in terms of how to operate it first and how to optimize it. It will be, I think, an interesting thing to analyze, and then to show you how, as Ravi mentioned before, it is our process knowledge what allows us to come with these solutions. There's no magic here. The only thing we do is get to know the process as best as we can and act on it. Now, to continue, then we will start with the methanol water impurities column. Just to give a little bit of background for the people who were not present in the previous webinar. Well, in this particular case, this is a methanol water column for a methanol production plant. So a methanol plant in itself, it means that the feed to this column is what comes from a synthesis reactor. That synthesis reactor is basically taking syngas that has been produced in a steam reformer. So there's a steam reformer that produces syngas. The syngas goes through a catalyst in a synthesis loop and converts that syngas as basically carbon monoxide and hydrogen. It converts it into methanol and water, and there are some byproducts, and that's also where it gets a bit more complicated. So because this was a very high purity specification for the product, that's when it became really challenging. So ultra high purity product, very high energy requirements because of the same. Flat temperature profile, we will see. I mean, if it's a high purity column, you can imagine that the temperature profile across the column can be very flat, especially close to the ends. And as I said, there were some impurities that you could not have in your product that you had to take out, which means you had a side stream into that column. And all that adds complexity to the situation. So here it is, a little schematic of our methanol water column. We have three main components. Let's call them components. One is methanol, the other one is water, and the other one are hydrocarbons. Those hydrocarbons are in particular heavy alcohols that have been produced in the synthesis part of the process. So you need to take them out. So we're talking basically about ethanol, propanol, heavier alcohols, and you need to take them out. Because you also cannot send them with the water. The water has to be treated, and for it to be treated, it cannot contain such substances. So you see, you have here three different streams coming out of the column, and added complexity here. The specification for this product is for it to have maximum 10 ppm of ethanol. So in a percentage basis, well, you do the calculation, how much is 10 ppm, right? So it means the purity that is required is a purity of 99.999 something percent of methanol. So obtaining such purity, it's not easy. It requires a lot of energy. And at the same time, making sure that you're obtaining such purity is challenging in itself. For which you can imagine that the way this column is operated, or used to be operated, was a bit exaggerating the reflux ratio in the column, so then you could always make sure that you were meeting your specification. But that in itself created a problem, which was excessive energy consumption. So again, a bit of background of how the column was configured, or how the base layer controls were configured by us initially, and then after we put the APC on it. So first, these were the configurations we did. Let's just try and understand. So we have the feed controller is actually a slave controller for a temperature controller in a sensitive tray in the column. This sensitive tray is the tray where the impurities are being taken from. So guaranteeing that you have the correct temperature in that tray was also a guarantee that you were taking out as the majority of the impurities. And as you can see, it's just not a simple temperature controller. It's actually a pressure compensated temperature controller. Means that even if the pressure changes, you could always make sure that the composition of that sensitive tray is as constant as possible. Why did we have to do that? Because as you can see, the pressure controller acts on a series of air coolers. This project was done in a very hot place. I'm not going to name the country, but let me just say that temperatures of 50 degrees outside were commonplace during summertime. So when those situations are reached, then usually what you have is you reach also the limit of your air coolers, and without much for you to do, the pressure of the column itself increases. So it's important to always keep the composition constant, even if the pressure of the column cannot be fully controlled. So what's going on here is that this pressure controller is using the feed to the column as means of internal reflux for the bottom section, and that's how the temperature is controlled. Then at the same time, we have a control of the steam. This is basically this FC, this flow controller, it has a strange configuration, which I'm not going to go into much detail, but just to keep it simple, just think of this as steam going into a reboiler, providing the heat needed by the column. And then as well, since to guarantee that you're taking most of your impurities out, then the flow controller that is attached to this side stream is in fact in ratio with the feed, meaning that if the feed changes, then this immediately changes to accommodate for that. And last but not least, in the top of the column, your control is not just a simple reflux control, but in fact, this control is a reflux ratio control. So your reflux ratio is always in control. Here, the configuration is such that your level controller is dictating how much the reflux moves, and then your reflux ratio controller is dictating how much top product you are taking out from the column. So this is already, let's say, complex enough, but then if we add to this the fact that we need to meet the specification of 10 ppm, well, then it becomes even more complex in that sense. So, then in terms of base layer, what was done is, as I just described, pressure compensated temperature, tighter level controllers, and feed-forward actions. But here, what's important to point out is the fact that we have a very flat temperature profile. So if you want to meet a specification of 10 ppm in the top, I think you can already imagine that you have to forget about the idea of finding a sensitive tray in the top of the column that you could use as an indication of your purity. A methanol water mixture with 10 ppm of ethanol or water, or with 20 or even with 100 ppm, will most likely have almost exactly the same boiling temperature, which means that for the majority, for most of the trays, I think it was the first 30-something trays, this column had in total 120 trays, if I recall correctly. The top 35 trays or so, they were all showing you exactly the same temperature. I mean, with changes in the third decimal figure of your temperature indication, which is most likely within the margin of error of measurement itself. So trying to use a temperature here as a way of trying to calculate or estimate your impurities was going to be really difficult. So what did we have to do? Well, what we had to do was just go back to our chemical engineering classes, and then remember very simple concepts that sometimes you can just take in use. So this is a very simplified approach, what I'm showing here, but basically what we're saying is that for any distillation column, this is for all of you who are chemical engineers, you will remember this is the famous McCabe-Thiele method of calculating trays in a column, or of calculating composition if you have a given number of trays. So here what we can see is the following. If this is your equilibrium line, and your green line and your purple line are your operation lines for the stripping section and for the recovery section, then what happens is that if you can change the slope of these operation lines, then it means you also change, with the same amount of trays, with the same amount of stages of separation, you also change the amount of separation itself. So that's why when you need to cut deeper, you put more reflux. When you put more reflux, basically what you're doing is you're changing the slope of this green line here. And in the bottom, when you change the amount of steam, when you change the amount of heat, or at least the heat to feed ratio, then you change the slope of this curve. So it means that both of them would have an effect on the purity that you get in the top column. And that is a very simple principle that we used to create a soft sensor, an estimator for the amount of impurities in the top of the column. So that's exactly what we did. So we just used the reflux ratio and a steam to feed ratio. Again, basically resembling those two operation lines that you see here. And that was enough for us to have very, very good correlations. What you see in red, those are lab data points. And what you see in brown is the prediction. This is a steady state prediction of the quality. As you can see here in the scale, is a scale from 2 ppm to 7 ppm. It sounds incredible, but actually you could get to that accuracy in this case. So it meant that just by using those two values, we were able to correlate them to the amount of impurities in the top. All right, and with very good degree of accuracy. Let's say within a 1 ppm degree of accuracy, which is, I think, good enough. Then once we managed to do that, then we thought, okay, now that we have a tool to estimate the amount of impurities, then we should pursue the optimization in itself. So I think it's probably clear for most of you that the optimization here is to try and, or the optimization direction here should be to try and maximize or go to the maximum amount of impurities allowable. Well, 10 ppm is the actual requirement from the client, so you will never try to get exactly 10 ppm because it's just too close. But you could go to 7 ppm, you could go to 8 ppm. What you see here is that in average, the way the column was operated was that almost always the amount of impurities in the top was around 2 to 3 ppm. Means it was a bit exaggerated. Of course, they were just guaranteeing that it was always going to meet the requirement. But if you have something that accurately helps you to estimate the amount of impurity, then you can start to, try to push it towards your real constraint. And that's exactly what we did here. We just built that soft sensor. And after we built the soft sensor, then we started finding the dynamic step response curves for each one of them. So just to give you an example of how the multivariable problem comes here, because you could say, okay, well, then it's simple. Then I put my soft sensor, right? And then my soft sensor, it will just be enough for me to start reducing reflux until I get to my maximum allowable impurities. You don't need APC for that. And I would say, initially, maybe yes, but remember that the steam to feed ratio also has an influence in the impurities. What happens here is something that you need to be remembered. Let me just go quickly back to this one. If you remember, the feed to the column was used as means of an internal reflux to control the cut here in the bottom. The sensitive tray temperature in the bottom, which you actually have because you're not getting the same amount of purity here in the bottom as you get in the top. I mean, you're looking for high purity in the top, but not for high purity in the bottom. Then you do have a section in which, and you can see it here, it's basically this section around here, where the temperatures actually do change if the composition changes. So you do have a sensitive tray temperature, but to control that, you use the feed to the column. And because of that, then it means that if you want to keep the feed to the column constant, which is most likely one of your objectives with any kind of control, then you need to make sure that you react to these to disturbances. So what happens is, since the feed to the column is attached to the temperature, then any changes you do either on the steam to the reboiler or on the reflux ratio, both of them will have an effect on that temperature, and both of them will make the feed to the column change. So then you start seeing interactions. And those interactions were the ones that we had to consider in the multivariable approach. So this is one of the main things why an APC was justified there. Not just the fact that we built a soft sensor, which in itself could just be used as a standalone feature and then try to use it somehow to drive the optimization, but also because it wouldn't be as simple as just creating some kind of control around that, some kind of, let's say, single input, single output control around that soft sensor, because the interactions that you had to deal with were a bit more complex than that. So this is just a screenshot of the, let's say, densest part of that matrix, of that multivariable matrix that the APC had to deal with. So you can see how, for example, the reflux ratio in this case affects your column feed. If you increase the reflux ratio, the column feed decreases, of course, because what's going on is you're cooling down the column. The temperature, as you remember, the sensitive trait temperature goes down, so you need less internal reflux, so then the feed goes down. But then at the same time, when you increase the reflux ratio, your impurities go down. And when you increase the reflux ratio, the impurities the impurities in the water increase. Obviously, you're sending more stuff down. So if it gets purer in the top, it should get dirtier in the bottom, and that's exactly what happens in this case. And then when you have the steam, for example, in the case of the steam, then same thing. If you increase the steam, that has an effect on the column because the temperature increases, then you need more feed to keep the same temperature. But then at the same time, as we saw, when you put more energy into the process, then you get better separation. So that's why when the steam increases, actually the impurities decrease. It sounds a bit counterintuitive, but when you think about it, it actually makes sense. So these kind of interactions, you need to consider them all the time. So if your objective is to try and maximize the amount of impurities in the top, this column right here, but at the same time, you want to keep the feed to the column constant, and you want to keep the impurities in the bottom, as constant as possible, then you can imagine that there is no way you can use a single input, single output approach for this kind of problem. You do need to use a multivariable approach, because in that case, it's actually both the reflux and the steam who are controlling both the feed to the column and the impurities. It's not one dedicated to one and the other one dedicated to the other. No, changes in one affect both of them, so the other one has to react to both of them, and then it's just a real multivariable problem. And that was the case, and we actually did manage to do a nice. So I'm using the same gains that you see here, which were the same process gains that we found when we did the model identification and back then when we made the project. So using these gains, you can, once we share the slides, you can do the calculations yourself just to make sure that I'm not saying the wrong thing. But basically, with these process gains here, what did we gain? We gained the following. So we had a reflux ratio, which was initially 2.15, and it went from 2.15 to 2.05. And well, that was quite significant. Why did it go from 2.15 to 2.05? Well, because we allowed the controller, the APC application, to keep the impurities in the top, the ethanol in the top, not at the typical 3 ppm value that they were controlling, but we allowed it to go all the way to 7 ppms, which was still safe, because remember, it was 10 ppms is the maximum allowable amount of impurities in the top. And while doing that and keeping the feed to the column constant, what did we gain? Well, we had less reflux ratio, but at the same time, to compensate for the changes in feed, you had to put less steam. And overall, this is a figure in tons per hour of steam. We had a reduction from roughly 70 tons per hour of steam, all the way down to 63 tons per hour of steam. So you could say that an increase from 3 to 7 ppms in impurities provided savings in steam of about 10%. And this is important, right? 10% savings in energy. If you're paying for that energy, which you typically are, this is just steam, which means there's most likely a boiler generating that steam. So that reduction there immediately translates into less fuel gas into your boiler. Well, there you go. That's money that you can make use of, right? And again, it's not as simple as it seems, because you have all these interactions. But bottom line, what allowed us to do this was the fact that we got to know the process enough. And that's why we managed to do it. We had the chemical engineering knowledge, for example, to know that to build a soft sensor there, we had to use something different than just temperatures, because they were never going to work. And yeah, that was the final result. Right?
Hey, JC, one quick question before you go to the next one. Somebody asked, what is the time to steady state in this column? And how does the percent impurity in the feed change?
Yeah, the time to steady state, as you can see, is roughly 3 hours. Yeah, give or take. That's the time to steady state. In any case, of course, we built what we call a steady state soft sensor. So it's based on the changes on the inputs to the calculation. So maybe if you were taking samples, then you would have a little bit longer time to steady state, but the dynamics inside would make it a bit longer. But for control purposes, this was long enough for us to keep good control. So that was the time to steady state, around 3 hours, as it says here. And then the other part of the question was,
does the percent impurity in the feed change? And if that's that, how does it impact the control?
The percent impurity in the feed, yes. Yeah, it did change to an extent, not too much. But yes, the percentage of impurities in the feed did change. But it was impacting mostly the sensitive tray and the amount of impurities that you need to take out. So sometimes it was needed to, let me just quickly go back. If you see here, we have this ratio controller here. So this ratio controller here was the one that operations needed to touch in case they started seeing some buildup of some other impurities. So then you take out a little bit more from the column just to keep those impurities in control. But yeah, that happens. But this is very down in the bottom of the column, let's say, because we're talking about tray. Well, if you count trains from bottom to top, we can say that this side draw column and the corresponding temperature, those were in tray 35 or 40 out of 120, means that you still had 80 trays from there to the top. So basically, whichever amount of ethanol arrived to the top was, I wouldn't say independent of the feed, but yeah, I mean, you were pretty much sure that whatever was coming was just because of the thermodynamic nature of the mixture. But yeah, there were little changes indeed. Yeah.
Thank you.
Right, and then let me go to the next example. This is why I chose only 2 examples. It already took 20 minutes to explain the first one, probably more. So for the second one, it's the extractive distillation column. So it's not as, again, here the complexity is a lot about how the column is not intuitive in the way it behaves sometimes. So the process in itself is an extractive distillation column that has benzene, so aromatics and non-aromatics, but you need to break whichever azeotrope that is generated between that mixture using solvent, which is normal in extractive distillation column, and in this case was the NMP, N-methylpyrrolidone. So that's what's used in this column to break the mixture, and then just separate non-aromatics from benzene product in this particular case. You had both requirements for top and bottoms. In the top, you wanted to have non-aromatics with a maximum amount of benzene of 3% tops, and then in the bottoms, you wanted to have basically just your solvent with the extracted benzene. And then the solvent then was, of course, recovered in some stripper column downstream. It's basically like a cycle, which then was recycled back to the column. Steam is used in this reboiler, meaning that the energy that this column needs is an energy you pay for. So it's important in this picture in terms of how you optimize it. So this is basically an overall view of the system, of the process. You see, you have your solvent coming in here. You also have a reflux coming in. So you have both. And this is when you need to start, thinking about, okay, this is not your average distillation column, because you have a solvent, but you also have a reflux. And there is a tendency for people to believe that, okay, because this solvent is coming in the top, then it's doing the same thing as a reflux is doing. Wrong. You start wrong if you think that. It has a very different function for the whole separation, right? Here is the function of the solvent is to extract, not to cool down, which is the function of the reflux. So that in itself already starts giving you an idea that, okay, this is not average. And then as well, you have for the rest, it seems like very standard, but remember, you have several liquid phases in this column. So the different liquid phases makes the whole column, it cannot behave exactly as you think it would behave. So one of the first things we did, and again, this is for the people who were not present in the previous webinar. What happens here is that the first problem we faced was the fact that they were trying to control the sensitive tray temperature in the top of the column. And I mean, you guess, what did they try to use? I can show you here what they're trying to use. Well, actually, this is after the modification, but initially, what they were trying to use to control the temperature of the top was, in fact, the solvent flow itself. Just let me show you here. Anyway, that was in the previous one. Just wanted to refer to you. So tell you that they wanted to control the top temperature, the sensitive tray in the top of the column with the solvent. That didn't work really well. Did not work at all, actually, because again, the job of the solvent is not exactly the same as a reflux. And then for the reflux, they had also some limitations. So that's why they were trying to use the solvent, but it was just not working, because it's not doing the job that you want it to do. So what we discovered while doing this is that, in fact, although this is tray 49, so way up the column, it is the steam to the column which had the biggest impact in this temperature. And that is the change that we proposed and we implemented there. So the temperature controller for the top was no longer using neither the reflux nor the amount of solvent going into the column as a means of controlling the temperature, but we changed it for the bottom. Why? Because it was the variable that had the biggest influence in this temperature. And I know it was not the closest, and it definitely has some delay when reacting, but you can believe that the performance was better. So it gives you a good control of that cut point, that maximum amount of benzene, for you to do controls more related to a separation index. It's always good to have in any single distillation column not only a measure of your product qualities, which is very important, of course, that is very relevant, but it's also good to keep an eye on variables that show you the degree of separation. And in this separation was to be able to control the solvent to benzene ratio. That ratio was giving you somehow an idea of the degree of separation. Just like, for example, in the previous example, the reflux ratio or the steam to feed ratio, those are variables that give you an idea of the degree of separation. Or in a stripper column, the delta T across the stripper column gives you an idea of the degree of separation. So those values in itself are not telling you the composition or the amount of impurities in your product, but they're telling you at least how good your separation is being done. So this is what is done here. So with that, it allows for control of both top and bottoms. This is after we implemented the control. You can see how, for example, when a set point change was done in the tray temperature, acting now on the steam, not like before on the solvent, but acting on the steam, when you did the change, you see how, for example, the steam, the first thing it does is this green one here. First reaction is to give your typical proportional kick, but then after it has to kind of come back, obviously, because there's some dead time. But this was just to accelerate the control. But this gives you a lot more tighter and more reliable control than what you used to have before. So once you have that, and once you have a base layer configuration that you can rely on, that is actually helping you to reject disturbances properly, then that's when you can think of moving forward and doing your APC. So that's exactly what we did here. So after we had better and tighter cut point control in the top and better control of the benzene, then it became easier to optimize and it was APC ready. So what did this APC application was about? Well, you can see here also the time to steady state here is even longer. Here they had analyzers that helped know the composition, so we didn't have to create any kind of soft sensor. So there were analyzers telling you the percentage of benzene in the top, and they were also telling you the amount of non-aromatics in the bottom. So those analyzers were working quite fine. But it also showed that your time to steady state was in the order of 4 hours, roughly. So it takes time for it to be controlled. So that could be one of the reasons why you most likely would not be able to do this control with a simple single input, single output control. Let's call it like with a PID control, you would never be able to keep a good control of these two compositions. It's just not practical, or almost, I wouldn't say possible, but it's definitely not practical. It will never behave the same way that it could behave with a model-based control, which is what we apply here, model-based predictive control. And then what we can see also here is the amount of interactions that we need to consider. So for example, when the feed to the column was changed, then immediately the amount of impurities in the bottom changed. When your feed changed, your ratio between solvent and feed changed naturally. I mean, it's the ratio in itself. The delta P of the column, which here was a constraint because they were operating very close to the maximum capacity of the column, increases. And of course, your steam consumption increases. And so on and so forth for the other variables. The solvent, the NMP, well, it definitely had an impact, for example, in the bottom composition, in the ratio with the feed, of course, but then as well, the solvent in itself, it had to go through a temperature controller to keep it as cold as possible for it to work as good as possible. So yeah, using it too much meant that maybe you would not be able to cool it down as much as you could. The solvent is in any case a liquid going in the column, so it meant that your column delta P would increase, driving you closer to the constraints of the plant of the column. In the steam consumption was also increased by that. And same thing we see with some other variables. The reflux, for example, yeah. Oh well, the tray 49 temperature, if you remember, this one acts on the steam. We knew for a fact, this is what we just said, that this 349 is very strictly correlated to the benzene content in the top. So of course you see a very clean response, but as well, because this 349 temperature controller is acting on the steam, naturally it will also affect the bottom quality. The more steam you put in, the more vapors going to the column. So it means your column delta P also increases. And you have all these kind of interactions that makes you think, okay, if I want to really try to minimize the amount of energy consumption or maximize the production, whatever it is that I want to do, I really need to know what the effect is. Because if you think about it, here we're doing kind of the opposite, as you typically would do. You are using the steam in the bottom to control the top quality, if you see here, because these other two models that we have, these other two models we have here with the solvent are just dynamic models. They don't have any steady state gain, obviously, because you have a temperature controller there. But anyway, means that in that case, you cannot use nor the reflux nor the solvent to try and control the top quality. And you say, oh, what? So you see, it's already getting counterintuitive. To control the top, you use the steam in the bottom. And obviously, to control the bottom, what do you need to use? Well, then you need to use the reflux in the top or the amount of solvent. So this is already something that makes you think, okay, this is a different problem to your usual problem. And then if on top of that, you need to take care of constraints in the column, then you know that if you want to optimize it, this is a very multivariable approach that you need to take. And this is what I want to show you here. So in this particular case, again, I took the process gains from what we identified originally. And with those process gains, you can make the calculation. So basically what I'm saying is, let's suppose you want to change your feed 1 unit, whatever it is. And then if you want to change your feed 1 unit and you want to keep constant your bottom, impurities, you want to keep constant the ratio between the solvent and the feed, which we said is important to keep constant because it's a measurement of the degree of separation. And if you keep constant also, for example, this valve, let's suppose you're very close to the constraint where you cannot cool down anymore your solvent. If you want to keep all of them constant, what would happen if, for example, I increase the feed 1 engineering unit? Well, to keep these 3 constant, then what will happen is, first of all, the solvent itself will have to increase to keep the ratio, right? The temperature will have to, the temperature of the solvent will have to increase to keep the cooling capacity of the solvent within control. And the reflux to the column will have to increase as well, because if you increase the feed, when you increase the feed, what happens is then you get more impurities in the bottom. And if you get more impurities in the bottom, then in this case, this is what helps you control those impurities. So all in all, what we see is that by a single increase of one unit in the feed, we see that both the column delta P, which is your constraint for maximizing production, and your steam, which is your constraint for optimizing energy consumption, both go up. You say, okay, well, I cannot always gain. If I'm maximizing, I cannot always gain. But then the interesting thing comes here. If you noticed, I purposely put 0 change in that tray temperature that we have been talking about the whole time, the one that uses the steam. So basically, the amount of steam changes, yes, but it doesn't. But in this case in particular, it's not changing because you are changing the tray temperature. It changes because of some other things. So what do you think we should do with this tray temperature? Should we maximize it? Should we minimize it? Let's suppose we want to minimize the energy consumption and we don't care that much about the increase in production. So instinctively, the first thing you would say is, oh, okay, if I want to save steam, well, sorry. If I want to save steam, what I need to do is reduce this temperature, right? If I've reduced the temperature, then I consume less steam, and that's exactly what this model is telling you. We can see here. The more the higher the temperature, the higher the amount of steam that you'd require. So it seems almost logical that if you decrease this temperature, then you would save steam, and then you decrease it against some purity constraint. That should be fair enough. But is that really the case? So when you take the whole matrix in consideration and do the calculations, let me show you what happens. I need to, sorry. I just need to do this 1 second. I need to open the spreadsheet. I wanted to embed this spreadsheet in the... So let's play with the spreadsheet just a tiny bit. Ravi, could you tell me if the spreadsheet is now visible?
Yes, we can see the spreadsheet.
Okay, good. So first assumption, okay, we want to optimize this column. What shall we do? Let's minimize this temperature. So let's reduce this temperature 1 degree and see if it's having the effect that we thought it has. So a change of -1 would be required. So if it's a change of -1, what will happen? What's this? So if I change this temperature and decrease it 1 degree, both my column delta P and my steam consumption go up. How could this be? Does this make any sense? Well, devil's in the details. And what happens is, if you look at this model in particular, which is the effect of the bottom of this tray temperature in, if you look at the effect of this tray temperature in the bottom composition, then you see it's a huge effect. It's a huge process gain. So it means that if you reduce that, if you reduce that temperature, it means you're putting less steam into the column, okay? But that reduced amount of steam into the column means that the impurities in the bottom increase a lot. And to compensate for that, you need to put a lot of reflux into the column. As you can see now, it's increasing 17 engineering units, the reflux, just to compensate for that. So then you say, oh, okay, so this is not the way to go. This is not the way to go, because although it seems like, yes, the isolated effect of reducing the temperature in the steam would be to reduce the steam overall, because a lot of other things need to be kept constant and controlled, then the sum of the effects is actually worse off. It makes it worse off. Whereas if in this case you increase your temperature by 1 degree, oh, surprise, surprise. Turns out that increasing your temperature by 1 degree, in this case, both helps you reduce the column delta P and the steam consumption. It sounds very counterintuitive, but again, this was a column that I told you from the beginning is counterintuitive. But then, yes and no. You can also argue, okay, well, what's happening here is that as you increase the temperature, what you're doing is basically shifting the impurities to the top. So obviously, doing this change of 1 degree in the top will make the impurities in the top to go up as well. So you need to have that margin of maneuver to be able to do that. But we said that for the top, the specification for benzene was 3%. So if you were operating at something like 2.5%, well, instead of running at 2.5% impurities, we'll try to run against that limit of 3%, because running against that limit of 3% will allow you to increase your temperature 1 degree. Yeah. So yes, okay, you're, let's say, very close to your purity limit, but at the same time, this is allowing you to both save steam and reduce column delta P, which in both cases will help you push more production through the column. All right, so I think that's basically the end of this example. Conclusions very quickly. So first of all, never forget that heat, material, and even hydraulic balance should always be reinforced by any kind of control that you do, either if it is just purity control or if multivariable control. Knowledge of process interactions is key. I think I just showed you. if you're not aware of all the process interactions, first of all, you will not be able to control it properly. And second of all, you will not be able to optimize it properly because you might be doing the wrong thing. Composition control is advisable where possible, obviously, yes. Sometimes you don't have analyzers, and then happens what happened to us in that first example in which we had to build a soft sensor. But why did we do that? Because composition control is advisable, right? And sometimes you don't have a temperature that you can just use to guarantee your composition. But as I said also before, a measure of the degree of separation gives robustness to an APC design, in general, to any kind of control. So if you have some kind of measure that tells you, okay, maybe I'm not seeing the composition itself, but at least I know I'm separating as good as possible, well, that is always good. Ratios are typically something that gives you that, or delta temperatures, but something that shows you how good your separation is at the moment. And then analysis of the possible trade-offs must be done as accurately as possible. I just showed you these trade-offs, although instinctively or intuitively you can think that the optimization should go in one direction. Well, be careful, because if you don't account for all the effects, it could actually be the other direction what benefits you. And then your optimization strategy will be a lot clearer if you do a good trade-off analysis. All right, that's it. Thank you.
Hey, JC, thank you very much for that deep analysis on distillation column controls. For everybody, please use Q&A session to ask your questions. In the meantime, I'm going to initiate a poll here. We would like to get your opinion on other topics that you would like to hear from us. Here we have chosen 5. If you like all of them, you can choose all of them. If there is something that we missed in this list and you would like to ask, please type in the Q&A session. We will take into consideration about that. Yep. So really appreciate you taking through this poll, and I'll publish these results of what's in the poll. And also please take some time to ask any questions. JC, there are a couple of questions before I'll let everybody answer these questions, this poll, and then I'll ask you those questions.
Okay.
Yeah, looks like the top 2 I'm going to publish here. The top 2 items, obviously the form is to troubleshoot APC applications. It's one of the top one. The second one is tips and tricks for PID tuning. And the third one obviously is how to do APC benefits. So we will take this into consideration when we announce our next webinar. Please look out for that. All right, let's see. Here are a couple of questions that came through. So what did you use to set the stream from the overhead? I'm assuming this is for the second example.
To set which stream of the overhead? Yeah, let's see. Are we talking about the solvent?
Yeah.
Well, the solvent is basically the job of the solvent is to stay in ratio with the feed.
So he asked a clarification question. It's saying that what did he use to set the stream for the non-aromatics?
For the non-aromatics. Yes, I mean, there's an analyzer there measuring the amount of benzene in the top.
Okay.
And then, but that is controlled with the steam, curiously enough. So yeah, I don't know if that answers the question. Yes, the non-arom in the top of the column, to keep the amount of benzene in control in the non-aromatic stream,
Yeah.
it is the steam in the bottom that is used.
Okay. It's basically controlled by the steam, and which controls the temperature, and that controls the amount of benzene. Okay.
Benzene in the top. Yes. Yes.
Yeah.
Indeed, yes.
Yeah. Perfect. Thank you. The second question is, in the first example, the condition, the number of gain matrix is 1 of 5. Did you mean to make the adjustments for ill conditioning? See 1
Here.
of 5 in the gain matrix. Yeah.
Yes. Okay.
I don't see the number.
Are we talking about the
105 here.
RGA number, the SVD number? Well, I don't know. It's not ill-conditioned, I can tell you that. But
can you go to the model itself? Can you go to the model itself? Is there
yes.
105 anywhere? I don't remember seeing 105. That's why. Maybe we'll take this question offline afterwards with this particular person.
Yes.
Okay.
Yes. Okay. Yeah, but I think I get what they mean. Yes. Did we do a gain matrix analysis? Yes, we did. And then did we make sure that there were no collinearities? We did make sure that there were no collinearities, and this was working without any kind of oscillations or shifts in targets. That's what you typically have when you're not making sure that your matrix is ill-conditioned or not. No, this one was working okay.
This is a difficult question to ask, but let's see if we can answer this one. What are the benefits of your APC compared to other APC systems in the market? So let me answer this question. This could be meant in a different ways. Are we talking about the APC software itself, or are we talking about the solution itself? So I think I would like to say we are not talking about software here, at least in this presentation. We are only talking about the solution itself. So I would say, JC, based on that, you can answer that.
Yes, I agree with you. In fact, one example was done with one technology and another example was done with another technology. The approach is the same at the end, is getting to know the process as deep as possible, doing the analysis as good as possible, understanding the interactions and handling the interactions. And that is independent of the technology that you use. So in that sense, yeah. I mean,
So
and even if we're talking about technologies, well, then yeah.
Yeah, to add to that, I think it doesn't matter which APC software we use. It is what matters is who does the APC. Does that person has good knowledge about the process and things like that? Yeah, thank you. All right, one more question. Many times there's talk about using automated step testing, which is good for some of these simple columns. But is this good for these complex columns also? What is your take on that?
Yeah, well, when you use automated step testing, there is one thing that you need to always consider, and is the fact that the steps need to hold for a time, or need to be held for a time that is as close as possible to the time to steady state of the process. So when you have simple columns that have quick time to steady state, then yes, chances are you are able to do an automated step testing tool, and that should be fine. And also when you don't have a lot of interactions. But since when you use an automated step testing tool, you need to use a seed model, which is not a very accurate model in itself. If you have a lot of interactions, then your automated step testing tool could start struggling. That's one thing. And if on top of that, your time to steady state is too long, then what happens in that case is that the automated step testing tool will try to hold the steps for as close as possible at the time to steady state. But chances are, since your models are not perfect and there are disturbances typically in the process, then chances are the automated step testing tool will have to start correcting the moves to avoid violating some limits. And then if there's some correction movements in between or during the time the steps are being done, that typically gives you not so accurate results. What you get typically is a kind of closed loop response. I wouldn't say it's a closed loop response, but at least what I can tell you is that your process gains will most likely be underestimated. So these automated step testing tools should be used with care in these complex columns because of time to steady state and interactions.
Yeah. So having the knowledge about the dead time, having the knowledge about how this particular columns react is quite important in designing these step tests.
Oh, definitely. Yes. Yes.
Yeah. Thank you. Well, let's see. One more question here. As we discussed in the previous webinar, and you emphasized here during this call, maybe I want to bring it out. If the base layer PID control strategy is not optimal, let's say, do you think APC can help, or should we go back to from design and try to fix the control strategy first?
Well, definitely you should try to make your base layer control as good as possible. Yeah, that would be my advice, to go and do it right from the beginning. If your base layer control is not working well, then chances of your APC correcting for that are not that good, especially because the main job of your base layer control is to reject disturbances that APC will most likely not be able to reject in a timely fashion. That's, I think, the what's most important here is about time. A PID controller runs every second, every half a second, depends on how you configure it. Obviously, if you have a CCC control, it's every 50 milliseconds or whatever. But then APC runs every minute, or it's a whole other order of magnitude in terms of how fast it responds. So if you allow the APC, or if you want the APC to do the job, that you could do with a PID control, well, you will most likely not get the same performance, right?
Thank you, JC. One more question here. Could you try to replicate these APC controls by just using some cascade loops?
Oh no, I don't think you should do something of the sort if you have very strong process interactions. Arguably, you could try to tune them, but the thing is, when you do that, then you will have to give up on one of the controls. The beauty here is it's a real multivariable control, so you can try and keep the controls as tight as possible, even if there's interaction between them, because you know those interactions. You can account for them even before doing the corrective actions. Whereas in the case of just simple PID cascades, they will always be acting on feedback. So it means that if you just configure a bunch of cascades to try and achieve the same result, you will have to make one of those cascades, or several of those cascades, slower than the others, because then only one of them can quickly react on feedback, and then the other ones just need to slowly react on feedback to accommodate for what the first one is doing. If all of them are acting as quickly as they can, then they will just exacerbate the interactions and most likely lead to unstable situation.
Thank you there. One last question. Okay. How do you make sure the plant is APC ready? I guess it is very difficult, but the way I would answer it is how we would do it. Yeah, go ahead.
How do we do it? This is what we do, right? This is the job we do when we try and start a project. How do you make sure that it's APC ready? Well, you go to the plant and you start checking everything. It's what we call a pre-test phase, or a benefit study phase. It depends on what you want to do initially. I mean, if you're convinced that you can have an APC that will bring you benefits, then most likely you already hired us to do the project. But then the first phase of the project, this is what we do. We go to the plant and we first make sure that the instrumentation is working fine. At least all the critical instrumentation is working fine, that all the critical and relevant PID loops are working properly, they're properly tuned, that the base layer strategy is properly configured, right? And only then, only when we have made sure, and also that the control system can accommodate an external, an external tool, and only when we have made sure of all of those things, then we can say is APC ready.
Yeah, so to answer that question a little shortly, there are two approaches. One would be to do a study during which time we will really go and analyze the plant and to make sure that it has all the necessary instruments and the instruments are working, etc. And in the second approach, you already know that you want an APC. And in that scenario, we would do this, but we will do this at the beginning of the project. So if there is a need to address some things, we will take care of that and then only come back for doing the actual APC implementation. Yeah, so I have one more question here. Do I always need analyzers for APC? And I think you touched upon how we can do in some cases without that during the talk, but maybe you can generalize that here.
Yeah. If you can have analyzers, yes, of course, by all means, use them. It is very useful to have analyzers. That being said, if for some reason there's not a chance of having an analyzer for some specific stream, there are ways around it, but not always. So, I mean, the answer is it depends. Preferably, yes. And if not, then you need to make sure that you can somehow have a good estimation of your quality at hand, because not all qualities are as easy to estimate as others, in which case you would definitely need an analyzer. But I think bottom line, it just goes back to one of the recommendations, or one of the conclusions is that composition control is always advisable, whichever the case is. Preferably analyzers in this, obviously, but if not,
yes, sometimes we take care of it using the lab results, but you need to have a reliable way of getting that, etc.
And even if you have lab results, you need an estimator that gives you, that estimates the value in between results, because the control doesn't stop. You need to do control all the time. You cannot just adjust every 8 hours, every 12 hours, every 3 days. For the control to be strict, you need to have constant feedback, let's say.
Yeah, good point. Well, one more question, a follow-up question to that. How do we build our soft sensors? Are they regression models such as black box models, or are they first principle based models?
Well, the way we do it is we try to first have as much as possible a first principle approach. So yeah, we use the outer engineering knowledge to see which are the variables that will help us estimate that property the most accurate way possible. Just as I showed you, like that in that the subsensor that we created with the reflux ratio, the boil up ratio, that in itself is somehow a bit of a first principles model. But now, that being said, when that is not possible, we build it. We have a tool called Inca Sensor that we can use to process data. So, and then we can, obviously with engineering knowledge, take a bit more of a statistical approach, and then find, usually what we find is a linear correlation between the inputs and the output. So we just take data, we take samples or labs results or whatever is the case, and then we correlate them to process conditions, and that's how we build it. But again, there's a lot of engineering knowledge that goes into that. It's not just it's not like we just take 100 variables and try them all and see which ones fit best, because no, that's not our approach. Our approach is always to think about the process first and then act.
Yep, that's a very valid point there. And in the amount of time you spend in doing that is a lot more efficient if you do it that way rather than just randomly taking the numbers. Yeah,
exactly. Yes.
Hey, with that, I think we have reached an end to this session. If you go to the last slide, please. Please go to the website, ipcos.com. There are many case studies, many webinars if you'd like to see what we have done in the past. Also, if you have any questions, you can send an email to that one. We will be sending out the link to this webinar at the end of today or maybe tomorrow. Thank you for participating and hope to see you next time.